In the last video, we've shown the analogy between dynamics as being described by the Hamilton-Jacobi equation and geometric optics. And we've got to the conclusion that in the same way that the geometric optics is a limitation for a more general formulation, which is called the wave optics, this dynamics as being described by the Hamilton-Jacobi equation is going to be a limitation for a more general formulation, which is called the wave mechanics. In this video, I'm gonna show the first step of how to get this. The first step of how to get this wave mechanics. Okay, actually, Schrödinger had this analogy laid down in front of his eyes. So just like right away, he wrote down the following ansatz for the possible wave equation for his dynamical system. He wrote down psi as a function of x and y and z equals a as a function of x and y and z as well, x and y and z, which is the amplitude, and that's multiplied by sine, and that's the postulate. Here's the postulate. As the phase of this wave function, he assumed the action here, because here the action here is analogous to the phase in here, right? So the phase of his function with the action, obviously. But actually he divided that by a constant k, because this action here has unit, and we know that the argument of sine has to be unitless, so we have to add this constant here to clear the units eventually. Now what he'll gonna do is easy. Just like, we know the form for this function s here. So the next step, just like to write this down in a more simplified way. Not simplified way, but actually to extend or to expand function x, not to expand, but just like to substitute by its value, which is w minus et, right, over k. So far so good. So this tells us that psi as a function of x and y and z is going to equal a as a function of x and y and z. From now on, I won't be writing this down like x and y and z, just like some time and space. W over k minus e over k t, right? Okay, so that tells us that psi, this time I'm just gonna write down psi without any action y and z equal a without action y and z sine w over k minus e over k t, right? So what now? Just like now, we'll make the analogy with the standard wave function form. The standard wave function form had the following. Assume for a moment it has the following form: p sine k, right, or minus omega t, right? That's the form for the wave function. So by analogy, this means w, which is omega, the angular frequency, is equal to e over k. So this tells us that we know that we can write down omega in a different way as 2 pi the frequency. So that's gonna be equal e over k. So right away, that tells us like here, e is equal to 2 pi k, right? But actually we know that this relation or this equation is right. We know that E equal h nu, right? We know about that. So this tells us right away that k has to equal h over 2 pi, right? Which we're gonna write down as h bar. So that was it actually for this video. Thanks for watching. I'm gonna continue in the video.